Hey, thanks, Arina, for the invitation and the presentation. So I want to talk today about a joint project with Jose Acevedo, Blekherman from Georgia Tech, and Cordian Riener from the Arctic University of Norway, which we put on archive 2 or 3 weeks ago. And it has this special title, The Wonderful Geometry of the Vandermonde Map. And this Vandermonde map is just the map consisting of the first power sums, and we consider this map on R to the n. And we say wonderful geometry since it has quite some combinatorial structure. So it's not a polytope, we will see this very soon, but it has like a combinatorial structure of a very special cyclic polytope. And originally, our interest in this topic stems from understanding non-negative symmetric polynomials, and we can also view a lot of those results in a different setting, not in a combinatorial or geometric form, but in this real algebraic way. So at some point of the talk, like in the second half, we talk more about non-negative symmetric polynomials, and at the beginning about this combinatorial structure. So if there are some questions, just feel free to ask it at any point. Let's recall some very basic notations, since they will be used a lot in this talk. We call a polynomial in several variables symmetric, even only if it stays invariant the same whenever you permute any of the variables. And as you know, when you have a polynomial ring in n variables, then the ring of symmetric polynomials is isomorphic to a polynomial ring in n polynomials, and you can choose, for instance, the first n elementary symmetric polynomials or the first n power sums. So a priori, none of them is better, none of those families of symmetric polynomials, since they are related by Newton's identities. So we have a polynomial relation between P and E, and also this polynomial relation is linear, so it gives you pk linearly in ek, but every smaller elementary symmetric occurs polynomially in pk. So this will be used a lot later, and at some point it's simpler to work with power sums and at some with elementary symmetrics, but often the results will translate. So another observation. So we consider now the homogeneous part of degree D of the ring of symmetric polynomials in several variables. The number of variables be larger than the degree. And then we choose now products of power sums as a vector space basis. And you see here some notation. So I have a P for a power sum, and then I write a subscript lambda, so a partition lambda, and this is just the integer partition of D. So when there's PAB, this should denote power sum PA times the power sum PB. And so we see that whenever the number of variables is large enough, larger than the degree, this vector space has always the fixed, the same dimension over R. So now let's start with some motivational problem. And we will present the proof just at the end, but as I learned in a math talk, you should always try to present your most important or your most interesting theorem in the beginning. So suppose someone gives you trace polynomial and several variables. So what is a trace polynomial? A trace polynomial is a polynomial expression in traces of powers of matrices for us here. So we can have trace of a to the k, but we cannot have trace of a times b. And we ask now whether this trace polynomial is non-negative if you insert any sequence of symmetric matrices, and they can have arbitrary sizes. So this might sound for you as an arbitrary question, but this occurs also in real algebraic geometry or also non-commutative algebraic geometry, real algebraic geometry, but they usually allow trace of A times trace of B times B. And what we show is that this decision problem is undecidable, and the key to the hardness lies really in this Vandermonde map. So we have to understand the geometry of the Vandermonde map, and then we can prove that this decision problem here, not for this specific polynomial necessarily, but for any polynomial in general, we cannot give an algorithm. Nobody can give an algorithm. This is an undecidable problem. So what is now this Vandermonde map? So we know that by nu indexed by the number of variables n and the degree, and it's a map from Rn to Rd, which consists just of the first d power sums. So x is mapped to this tuple of power sums evaluated at x. And how does it relate now to these trace polynomials? So you recall from linear algebra that if you're given a symmetric matrix, then the trace of this matrix is equal to the sum of the eigenvalues. So if we take now trace of a to the power d, then it's just the sum of the first of the dth power of the eigenvalues of the symmetric matrix. And now we can reformulate our trace polynomial from above into non-negativity. So we insert ABC symmetric matrices, and we replace it now by the power sums, by even power sums, P2, P4, P6. And we evaluate it now in different variables, x, y, z, where x corresponds to A, y to B, and C to Z, so to the eigenvalues of the matrices. And now you already see here why we restrict us to traces of A to the power D, but not to trace of A times B. And this is because there's no polynomial formula known where you can express trace of A times B for arbitrary matrices AB polynomially in the eigenvalues. So we go to the proof of this result later in the talk. But now again, why do we have to understand the geometry of the Vandermonde map? So we have again the same trace polynomial as on the previous slide here on the first line. And now we just replace the power sums, which we evaluated x, y, z, by some vectors a, b, and c. And now those vectors a, b, c, they are contained in the image of this Vandermonde map. And this lets us draw the following two conclusions. We are interested in the non-negativity of polynomials whose underlying variables are contained in the image of this Vandermonde map. Yes, here I use only even power sums. So this translates to the image of the Vandermonde map restricted to the non-negative orphaned. And second, we want to understand the behavior at infinity. So we want to plug in matrices of all sizes, and therefore we have to consider the limit of this increasing changes of images when n tends towards infinity, and the degree d is fixed. So this is the notation that I will use and some observations. So we restrict us here to the image of the Vandermonde map restricted to the non-negative orphaned. And this is because things get simpler, or the combinatorial structure is more interesting in this case here. So when we restrict to the non-negative orphaned, we can also restrict to the probability simplex. So as usual, I denote here the probability simplex by delta indexed by n-1 when it's contained in Rn. And then we consider the image of the Vandermonde map on the probability simplex, and we denote this by capital pi, again indexed by the number of variables and the degree. But here we omit the first coordinate because P1 of x, when x is contained in the probability simplex, is just the sum of all the xi's, which is equal to 1. So we omit this coordinate, and this is then something contained in R to the d minus 1. And why can we do this? So every power sum pi is homogeneous. So it's enough to understand the image of the Vandermonde map restricted to the non-negative orphaned on the probability simplex, because otherwise your element x is just of the form lambda times y, where y is contained in the probability simplex. Now this Vandermonde map is weighted homogeneous, so you can take out, based on homogeneity, you scalar lambda, and you have to understand the image on the probability simplex. And this is what we then call a Vandermonde cell. And we want to understand the combinatorial structure of this Vandermonde cell. Some observations. So this Vandermonde cell is compact and it's a connected set. So why is this true? The probability simplex is compact and we have a continuous map. Yes, and it's also connected. And those Vandermonde cells for a fixed degree, they are nested increasingly because you have more freedom. So you allow a new variable to choose not arbitrary, because you have to live in the probability simplex, but this last variable is either equal to 0 and you're contained in the previous image, or you have this new variable and you construct new images. So we have this increasing, and actually it's a strictly increasing chain of images of these Vandermonde cells. And when we want to understand the behavior at infinity, we denote the set by pi b. So we omit here the number of variables n, and this is then formally the closure of the union of all of those images, of all of those Vandermonde cells. And we are not the first ones who are studying those Vandermonde maps or Vandermonde cells. Actually, they have been studied by several authors before. So when we look in the literature, the first thing we find, or not really the first thing, since it's not that well known, I would say, is a paper by Ursel from the late 50s. And he actually studied several of the properties or theorems that we prove again. And we were just aware of this paper by Ursel like 2 or 3 months ago. And it's not that often cited. And it's also very long, and all of the proofs are in text form. Not all of the proofs, but there's a lot of text. And it's very hard to read this paper. It's not, it's of course also in some sense rigorous, but it's not like a today's math paper. And Ursul's motivation of studying this Vandermonde map and the image restricted to the non-negative orphan stems from understanding inequalities in LP norms. And then Arnold, Giventhal, and Kostov, they studied these Vandermonde sets, Vandermonde cells, but they considered the elementary symmetrics and not the power sums. And you have the Newton identities, so you have a polynomial diffeomorphism between those sets. So it's actually the same. And the motivation for them to study those sets stems from understanding univariate hyperbolic polynomials. So on the next slide, I will tell you why they are related to this set. And then more recently, people from the nonlinear algebra community in Leipzig studied the Vandermonde map or the even Vandermonde map, so restriction to the non-negative orphans, and they used tools from computational algebraic geometry. And this first paper here by Bigger, Pelinski, and Wageringel, they studied only the case d equal to 3, and they described the boundary of the set, and already this is quite some challenging task. And then Melanova, Sturmfels, and Winter, they have more general results, and they asked some questions. They didn't formulate it as a conjecture, but some questions like about this combinatorial type of this Vandermonde cell. This is something we give a proof for. And then these trace polynomials that I mentioned, they said they are studied not only by us, also by real algebraic geometers like Klepp, Pascoe, and Volcic. They provided a Positivstellensatz for univariate trace polynomials. And so what is a Positivstellensatz? So this is something in real algebraic geometry. If you are given a polynomial expression which is non-negative, then how do you verify that it's non-negative? And you can verify it, for instance, if you can write it as a sum of squares of some elements. And of course, there also can exist Positivstellensätze if a polynomial is strictly positive and not only non-negative. And here I use the word normalized trace. And this is when you replace trace of a matrix A by trace of the matrix A divided by n, where n is the size of the matrix. And this changes something. So we see this later. But now briefly about elementary symmetrics and the results there. So again, some new notation, and I hope it's still okay. So we had this pi for the image in the power sums, and now I use capital E for the image in the elementary symmetrics on the probability simplex, and ED for the image at infinity. And here you see some plots for the planary case. So we have d equal to 3, but E1, the first elementary symmetric, is the first power sum, and this is constant 1. So we omit this, and here we plot only E2 on the x-axis, and on the y-axis it's E3. And we see here N3 and N5. And we talk about this soon in the power sums. And something you can observe here is that what is on the lower part of this boundary, like these two arcs, they are also on the lower part of the boundary if n increases, if n goes towards infinity. But you always add some additional arcs here on the lower part of the boundary, and this upper part grows. So we have some phenomena for the limit here, but soon more details. But why is this related to hyperbolic polynomials? So one calls a univariate polynomial hyperbolic if all of the roots of this univariate polynomial are real. And you all know Vieta's formula, either from high school or from your first courses at university. So you're given a univariate polynomial and you write it as a product of the roots here. And then you can write it without knowing the roots, or usually you know this expression, and then there's a relation between the roots and elementary symmetrics. So this univariate polynomial is of degree L, and then you can write it as t to the L minus the first elementary symmetric evaluated in alpha, and then plus minus up to EL alpha up to some sign. And when we want to understand hyperbolic univariate polynomials, we have to understand this Vandermonde map in the elementary symmetrics on Rn, or in our setting, we understand it on R greater or equal to 0 to the power n on the non-negative orphan. And this limit has some, in some sense, natural explanation also for Kostov, because he says that this limit set ED is now the set of all vectors E1 to ED, which are extendable to a hyperbolic univariate polynomial, meaning that you can multiply it by some t to the k, and then you can add some other univariate polynomial of lower degree, and what you obtain in the end is hyperbolic. So you add a lot of different coefficients here at the end, and you extend the degree, and then you obtain a hyperbolic polynomial. So this is also some different direction for interest in this study of the Vandermonde cell. But now our first theorem. So understanding this Vandermonde cell is explicitly difficult, but we can say a bit about its combinatorial structure of the boundary. So we know that it's connected, and it also seems to be contractible, but therefore we don't have a proof. So it's contractible if you consider the image of whole Rn and not only of the restriction to the non-negative orphan. So, but what is now the boundary? Let's talk about it. So we want to understand the boundary of the Vandermonde cell, and we say it's the set of all evaluations of this Vandermonde map on all points of the probability simplex, which have some specific multiplicity structure. So it consists of at most d minus 1 different non-zero coordinates, and they are ordered increasingly. X1 is less than or equal to x2, and so on. And we have some multiplicity vector R occurring there, or S occurring there. And it can be of two types. So we have a lot of copies of 0, then we have one copy of x1, then a lot of copies of x2, one copy of x3, and so on. Or we have a lot of copies of x1, one x2, and so on. And all of those vectors R and the S, they give us in the end one patch. And the gluing of these patches will then be the boundary of this Vandermonde cell. So how do we prove this result of the boundary? So there's also a proof by Ursel going by induction, but we use or actually adapt this proof by Arnold and Kostov for the image on Rn. And how do we do it? So what one does is one considers so-called Vandermonde fibers, and those Vandermonde fibers, they are just the set of all x in the non-negative orphan, such that P1 is equal to some fixed A1 and PD minus 1 is equal to some fixed AD minus 1. And those fibers, they are either empty or they are compact and connected. And when we want to understand now the boundary, we have to understand the image of the last power sum on such a fiber. And it turns out that this image is either empty or it's an interval. And when it's an interval, then we have to understand the minimum and the maximum of PD on this fiber. And then the boundary consists of all of those minimum and maximum. And to do so, we have an analytic approach, or it's also the approach by Arnold and Kostov. So there's not that much new in this. So we set up a Lagrange function, and then we analyze the necessary, the sufficient condition. And the necessary condition, because we have power sums, will translate to a univariate polynomial of degree d minus 1. And this can have at most d minus 1 real roots. And this gives us this bound on the number of distinct coordinates here of some elements which are mapped to the boundary. And the sufficiency condition is then some condition on the so-called bordered Hessian, that it's positive semi-definite. And this gives us this multiplicity pattern. So these are some very analytical arguments, and they work for the power sums because the derivative of the power sum is simpler than the derivative of the elementary symmetric, but then you can translate by polynomial diffeomorphism to the elementary symmetrics. So now let's consider one example where d is equal to 3. Then we have d minus 1 is equal to 2. And we see, okay, there are only a lot of copies of 2, 1x1, and a lot of copies of x2 possible, or a lot of copies of x1 and 1x2. And then when we in this case, in the case 2, then there's also only one S vector, because we must have one x2 and a lot of x1s. But when we are in the first case here, we have a lot of R vectors, because we can vary. We can have a lot of copies of 0, just one x2, or a lot of copies of x2, and some copies of 0. So what does it mean? So when we plot now the image of the Vandermonde cell for the planary case d equal to 3, we observe the following. So we have one upper arc, and this upper arc here comes from the multiplicity type 2, because we have just one choice. We must take one x2 and a lot of copies of x1. And then analytically, we have that those x1s plus x2 must be equal to 1. So we have a parameterization, and we get this upper arc here. And for the lower part, we have now several patches, several arcs. And everything which is on the lower part of the boundary then remains on the lower part of the boundary. And I have to confess that those pictures are not that well made, so it's not too easy to see. So this arc, the very long arc here on the lower part of the boundary, is the same as this arc. And the next one is this one. This one is this. And then we have always one additional arc on the lower part. And in the end, when n tends towards infinity, those vertices of the set, they accumulate around the origin in the end. And what is this picture here in the planary case telling us? It tells us that the limit set, the limit on the Vandermonde cell, is not a so-called semi-algebraic set. So the semi-algebraicness definition or word stems also from real algebraic geometry. But what does it mean? It means you cannot define it as a Boolean combination of sets which are defined by real polynomial inequalities and equalities. And those semi-algebraic sets, they are important there for non-negative, for nicht-Negativstellensätze, so for certificates of non-negativity of polynomials. And yes, everything in real algebraic geometry goes back to semi-algebraic sets. And although we have a fairly simple map, this Vandermonde map, when we go to the image to infinity, it leaves this setting of semi-algebraicity, and things get more complicated in some sense. So some generalization, that's also what Kostov, Arnold, Giventhal talk about. We don't have to make those results only for power sums. So this transfers very simply to weighted power sums. So you choose some weights, W, which are all strictly positive, and you can also allow strictly positive exponents. So we don't have polynomials here. We have some functions, analytic functions. And then we take some positive exponent vector containing real numbers, strictly increasing, and the same boundary description from 2 slides before transfers now to this generalized Vandermonde cell. And why is this the case? Because first, the derivatives of those generalized sets, they are fairly simple again, the partial derivatives and then the gradient. And what we have in the end is a so-called generalized Vandermonde matrix. And since we work here with the probability simplex, we care about elements contained in a non-negative orphan or positive elements. And the necessary and the sufficient condition for the Laplace function in this setting here translates now very analogously, but now we have only solutions which are strictly positive of a univariate function, and then you don't argue about the number of roots of a polynomial. This is not possible, but there's a theorem which is called Descartes' rule of signs in real algebraic geometry, which allows you to make those results. And then you observe that for results on the boundary, you actually can only work with integer exponents because you can approximate reals with rationals, and the homogeneity of the Vandermonde map allows you to restrict to integer exponents. So this was the analytic part of the talk, and from now on it's more combinatorial, and in the end, yeah, it's more combinatorial from now on. So I said that the boundary of this Vandermonde cell has a combinatorial structure, and actually it has the structure of a cyclic polytope. So let me recall what a cyclic polytope is. So you're given 2 integers, n strictly larger than d, and d larger than or equal to 2. And then the cyclic polytope with n vertices in dimension d is the convex polytope with all the vertices are chosen as points on the d-dimensional moment curve. So here we have the moment curve, and then you take real numbers, t1 less than t2, less than up to tn, and then you take the convex hull of the relations of all of those ti's. And those cyclic polytopes, they have very nice properties. So first, the combinatorial structure, meaning the f vector, it doesn't depend on the chosen vertices. That doesn't matter. Then second, you don't have to use this traditional moment curve here. You can also take different moment curves. So you can also work with elementary symmetrics instead of this. So a bit later more. And McMullen proved in the 70s, and this then was generalized by Stanley in the 70s and the 80s, the upper bound theorem, which says that the cyclic polytope have the maximal f vector component-wise among all convex polytopes with dimension d and n vertices. So they're of interest also from a linear programming reasons, because we have a lot of facets and not too many vertices. So I mentioned the cyclic polytope is the convex hull of n points on the moment curve, and they are arbitrary. But for us, we take here the cyclic polytope as the convex hull of points on the moment curve, which are just the first n natural numbers. And I use an abbreviation. So k hat should now denote the image on the moment curve of an integer k. And another nice thing about cyclic polytopes is that their facets are characterized by the so-called Gale's evenness condition. So it tells us the following. The facets, so the facet sets k hat, k and s, so S is a subset S of N of size D, forms a facet if and only if it satisfies one of those conditions, and the conditions depend on the parity of D. So when D is even, S must be a disjoint union of consecutive integers I plus 1, or it's a disjoint union of consecutive integers with the endpoints 1 and n. And when D is odd, then it's a consecutive union of those, disjoint union of those consecutive integers with the endpoints. And now this was maybe a bit abstract. So here's a visualization that I took from Volker Keibel's and Wasmer's paper. So here we see first planary cyclic polytopes. So the dimension D is 2, so it's a different notation, and we have 3 vertices here. So we have a disjoint union of I plus 1, or of the endpoints. So this gives us here a description of all of those facets on this case. And here we have a 3-dimensional visualization. And now let's compare this with Gale's evenness condition. So we see here when n is 5, so this is the middle picture, we can count with Gale's evenness condition the facets, there are 6, and either we use the end vertex 1, and then we form here a facet, here and here, those 3 facets, or we use the end vertex 5, and then we can form those facets here. And when we go to higher dimensions, yes, I can visualize it that easily, but one can describe the facets by Gale's evenness condition. So Sturmfels, Minalova, and Winter, they observed in their paper by computational experiments that the image, the Vandermonde cell, the boundary of it, has the combinatorial structure of a cyclic polytope, meaning that it's a gluing of patches. These patches are deformed simplices. They are the deformed facets of the cyclic polytope, and the vertices of this deformed set, they correspond to Gale's evenness condition. And this is then something that we prove. And in their paper, they formulated like the boundary of the Vandermonde cell has the combinatorial structure of the cyclic polytope. This is what they observe, and they don't specify what they mean with it. So in our understanding, we mean with it the following. So there exists a very concrete homeomorphism, which maps the boundary of the cyclic polytope to the boundary of the Vandermonde cell. And this homeomorphism is actually a diffeomorphism when you restrict it to the relative interior of any phase of the cyclic polytope. And this is very important because when you don't use that it's a diffeomorphism, then you can just map it to a sphere, for instance. And the sphere, you would probably argue, doesn't have a combinatorial structure of a cyclic polytope. So we need that it's a diffeomorphism on the relative interior of the facets or on the relative interior of any phase. And here's another picture from their paper. So this is something 3-dimensional. And we see here some curved simplices, what they call it. And these are curved cyclic polytopes with n equal to 6, d is equal to 3. And all of those facets, curved simplices, they satisfy Gale's evenness condition. So 1, 2, 3, 1, 3, 4, 1, 4, 5, 1, 5, 6, and the same with 6, and these other integers. And the colors, they appear here because they observed in the Vandermonde cell, when you let go from n to n plus 1, then they always appear more facets. And this is what I demonstrated in the planary case, where we had more arcs appearing on the lower part of the boundary. And in higher dimensions, we cannot speak about the lower part or upper part of the boundary. And they're always from n to n plus 1, there will be more patches. But we still observe some limit behavior, which one can make very concrete And in the limit, one has actually that it behaves like an infinite cyclic polytope, but I don't go into details here. So how do we prove though this result? So you need to recall that the boundary consists of this union of all the points on the probability simplex xi less than or equal to x2, which have specific multiplicity structures. So we have some vector r, and this r is either of type 1 or type 2. And then we make sure you associate to each of those multiplicity type vectors r a simplex, just consisting of all of those points of the form, which values then sum up to 1. And then we make sure that you can take a union of all of those R simplices, and this union then, when you evaluate it correctly, gives you precisely the Vandermonde boundary of this Vandermonde map. Yeah, let me skip the proof maybe. So now I spoke a lot about power sums, and this was because the derivative, the partial derivatives, the gradients of those power sums are simple. And all the results still work for elementary symmetrics because you can switch. So E was the image in elementary symmetrics. And you can switch because you have this diffeomorphism, polynomial diffeomorphism by Newton identities. And this is not a linear map, it's only a linear map if the dimension is very small, if it's at most 3. And now we want to argue or give some arguments about the convex hull of the image of the probability simplex under the elementary symmetrics map, and the image at infinity for fixed D of the elementary symmetrics map. And you recall that you can write any symmetric polynomial as a polynomial in elementary symmetrics or in power sums. So here's a typo. One of those families, second, for instance, should be power sums and not elementary symmetrics. And a priori, none of those families is better. But here now, for it follows, when we consider the convex hull, the elementary symmetric polynomials are better than the power sums. And not only better, but some results do only work in the elementary symmetrics and not in the power sums here. So now we talk about non-negativity or copositivity of such symmetric polynomials, very special polynomials, namely hook-shaped symmetric forms. So what does it mean? So symmetric form means we have a symmetric polynomial which is homogeneous of some degree D. And then we can write it as a polynomial in the elementary symmetrics. And with this lambda notation, E lambda, we can write it as a sum over all of these E lambdas with some scalar, some real scalar AI in front. And we call such a symmetric form hook-shaped if all the partitions which occur in this expression here are hooks. So here we have just a lot of ones, so it's one column. Here we have one row. When we consider the Young diagram, and then one column, and the same here. So this is what we call a hook-shaped symmetric form. And in this hook-shaped symmetric form, we set the first elementary symmetric now equal to 1. So this is restricting, not really to the probability simplex, but also to the probability simplex. Then it also occurs that E1 is equal to 1. And when we do so, what we obtain is a linear polynomial in all other elementary symmetrics. So this is A1 times 1 plus A2 times E2 plus A3 times E3 and so on. So this is a linear polynomial in the EIs. And this linear polynomial is now copositive. This means it's non-negative on the non-negative orphan, even only if it's non-negative on the probability simplex. And this is because we have a homogeneous polynomial. And again, by homogeneity, we only have to check non-negativity now or the probability simplex. And then this is non-negative, even only if it's non-negative on the convex hull of the image in the elementary symmetrics, because it's a linear polynomial expression here. And this is our motivation to study the convex hull of this elementary symmetrics map. And we are not the first ones again who study it. So this set appears also in extreme limit graph theory. So Bolobas was the first who characterized the convex hull of the image of the elementary symmetrics on the probability simplex. So actually his proof was for the planary case, so d equal to 3, but then shortly afterwards in extreme combinatorics, it was observed that this extends to arbitrary dimensions. So we see that this convex hull is a polytope, and it's a convex polytope, which is the convex hull of n points. We have we consider also the image of Rn, or the probability simplex in Rn. So it's a convex hull, and it's the convex hull of those n points, which are now weighted points from this moment map here. And what do we observe about those vertices? Those vertices are actually the evaluations of the elementary symmetrics map on very special points, namely the vertices of the probability simplex when we restrict to the cone xi is less than or equal to xi plus 1. Namely, we have a lot of 0 copies and then k copies of 1 over k. So this gives us the convex hull and the vertices. And at infinity, this is some easy corollary then. You can characterize the convex hull of the image of infinity as a convex hull of countably many points. And of course, this is not a polytope, but it behaves very much like a polytope. And also later, I would be happy to discuss a little bit. So we looked a bit in the literature, but we did not really find arguments on those sets or papers on sets which are like a convex polytope with countably infinitely many vertices. So here, in this case, it's really a polytope, and it has countably many vertices, and they accumulate around this limit point. And on the Vandermonde cell at infinity, it's not a polytope, it's a deformed polytope. And at infinity, we have, again, infinitely many vertices. And maybe one of you knows, can give me some reference to objects like that. But so some observation, when we evaluate now power sums at the same points as the elementary symmetrics, then we obtain just the points on the moment map that we looked at before. So the first n natural numbers evaluated on the d minus I dimensional moment map. And although the Newton map between the e's and the p's is not a linear map for d larger than 3, we have a linear map between those specific relations of elementary symmetrics and power sums at those points. So what does it mean? It means that the convex hull in the elementary symmetrics is a cyclic polytope because it's a linear map, it's a bijection between a cyclic polytope. So because we have a moment map and we take elements from the moment map, and this tells us that this is a cyclic polytope here. And we also did not find in the literature explicitly that somebody mentions this is a cyclic polytope. Of course, it's not a big result because it follows just from this linearity of the map. But yes, it's worth to formulate, I think. This set is a cyclic polytope as well. And now just a reformulation from our motivation of understanding non-negative polynomials. So you're given such a very special hoop-shaped symmetric form in sufficiently many variables, then this is copositive, even only if the evaluation at those n vertices is non-negative. Because it's non-negative, even only it's non-negative on the convex hull of the image set. And you can also formulate it now for copositivity in any number of variables, and then you have to check on the countably infinitely set non-negativity. And this theorem or corollary here appeared in a paper in the 80s by Blekherman and Resnick in Decree 3, but actually they formulated for positivity, and this is because you can go from EI to EI evaluated in x1 to the 2, x2 to the 2, and so on. And then copositivity is the same as non-negativity, also called even symmetric polynomials. And in their paper, they study even symmetric sextics. So this is a three-dimensional vector space restricted to P2 equal to 1. It's a two-dimensional vector space. And their arguments, how they derive this result, are using trigonometric functions and some induction process. And with this, we give some more geometrical explanation of their results. And I said things go wrong when we work with power sums and the convex hull of the Vandermonde cell. And this is because here you have that the Vandermonde cell is actually not contained in the convex hull of only those special points. So these are the points that you would believe are correct if you work with elementary symmetrics, because those are the same evaluations. So P2 up to PD is now evaluated at the same points as the elementary symmetrics. But then we show that as soon as you go to larger degree than 4, when you don't have a linear relation, then the Vandermonde cell is not contained in this convex polytope any longer. And so the simple test sets for copositivity found by Blekherman and Resnick for even symmetric polynomials in power sums cannot be formulated for higher degrees. So now we come to the end, and I want to explain this undecidability result and why we can use the geometry of the Vandermonde cell for this. So I recall what a trace polynomial is. We have n variables here, and then we take traces and powers of those matrices, and we take a polynomial expression in those powers in traces of powers of those matrices. And here we only consider evaluations on symmetric matrices, but of arbitrary sizes. And what we prove is the following decision problem is undecidable. So your input is integer k, which is the number of matrix variables, and you input trace polynomial, and then you ask whether this trace polynomial is non-negative for any symmetric matrices of all sizes. And when you don't go to arbitrary sizes, then this is decidable because you have a semi-algebraic set, and there you have some arguments for this. So these are standard tools, and here this really occurs at infinity. But something interesting happens. So when we speak now about normalized traces, so this is the setting of Igor Kleb, Volchich, that I mentioned before in the paper on Positivstellensätze for univariate trace polynomials. They use normalized traces, and the normalized trace is just here denoted by trace tilde, the trace of the matrix divided by the size of the matrix. And if we do this, and then we just use the same theorem, but we use normalized traces and normalized trace polynomials, then we prove, this is one of the second big theorems, that this problem is decidable. So when we only care about a fixed dimension, so fixed matrix size, then those problems are equivalent. And this undecidability happens only at infinity and not before. So I will try to explain why this is the case. But what is a consequence of the theorem is that there cannot exist an algorithm to decide whether such trace polynomials are non-negative for all symmetric matrices of all sizes. And the proof that we use goes back to a proof of Hatami and Norin in extreme combinatorics. And there it's actually enough to have 12 variables. So we don't have to have arbitrary size of input variables, or this k here doesn't have to be arbitrary. K equal to 12 is sufficient, but it's not sufficient to take univariate polynomials. And also it's sufficient to consider only the first 3 even powers of matrices and traces in them. And this then relates to the Vandermonde cell that you saw before on the pictures, because this means we take P2, P4, P6, and then we evaluate it on the sphere because it's homogeneous, what we consider as something homogeneous. And instead of considering P2, P4, P6, we can consider P1, P2, P3 on the probability simplex. And then we understand the Vandermonde cell. So I mentioned this. So there's the paper by Hatami and Riener in extremal combinatorics. And what they prove is that so-called linear inequalities in graph homomorphism densities deciding their non-negativity is undecidable. And our proof follows very much from their proof. So there's not that much to adapt, I have to say. So only very few things. So what do? So we replace those traces by the first 3 power sums, and we have to check now copositivity. So we have to check non-negativity on the Vandermonde cell. But because D here is equal to 3, we have the Newton identities have a linear relation. So we can use the elementary symmetrics instead. And then we have this hook-shaped elementary symmetry form of degree 3 here. And this is copositive in all number of variables, even only if it's non-negative on the vertices of this convex hull at infinity in the elementary symmetrics. And we have countably many vertices. And Hatami and Riener, what they do is now they relate non-negativity of such an expression, such a hook-shaped symmetric polynomial on the vertices of, it's more or less the same set as our here at infinity, to non-negativity of polynomials on n to the k. And then they deduced from Matiasevich solutions to Hilbert's 10th problem that deciding non-negativity of such polynomials on k powers of the natural numbers is an undecidable problem. And from there, the undecidability follows. Actually, it's the other way around. So you embed Matiasevich problem into the problem of deciding non-negativity on n to the k. And so here again, we see this, for the first time, we see this convex hull in the planary case at infinity. So we have a lot of copies of the natural numbers here. Yeah, here not, it's actually n equal to 20, but I hope you can imagine that we can have copies of the natural numbers, and then we take k copies of the set. And if we have only k equal to 1, this problem is decidable, and this is because deciding non-negativity on the natural numbers of a universal polynomial is decidable. So what is now different in this normalized setting? It seems like a very small adjustment. So we just take a power sum and divide it by n, where n is now the number of variables. And the key to this is this theorem by Timofte from 2003. So this says something about testing non-negativity of symmetric polynomials. It says you're given a symmetric polynomial, then the symmetric polynomial is non-negative globally, even only if it's non-negative on points with only very few distinct coordinates. So the number of distinct coordinates can be bounded by half the degree if the degree is sufficiently large. So what does it mean? So let's denote this half the degree by kappa. And let's assume, just for demonstration, you want to check whether a power sum of degree k is non-negative, or such a power sum of degree k is non-negative in n variables. And then when we apply now Timofte's theorem, then we see that, okay, we can replace arbitrary a's in Rn by elements in R to the kappa, and we must have some multiplicities in front of all of those xi's. And those multiplicities, they are natural numbers, alpha I, and they must sum up to n. And when we now divide the power sum by n, we obtain that this alpha is contained in the probability simplex, but it's a rational number. And if we allow now arbitrary sizes, arbitrary n, then we can approximate any or we have any alpha in the intersection of the probability simplex with the rationals. And by this, we know that testing non-negativity of such a normalized trace polynomial at infinity is equivalent to testing non-negativity of a polynomial on the direct product of the probability simplex and R to the K. But this is a semi-algebraic set, and one knows that testing non-negativity on semi-algebraic sets is decidable. And from this, you deduce that in this normalized setting, things are decidable. And this is the last slide. So just one more thing I want to mention. So there's a paper by Jose Acevedo and Blekherman, and in their setting, they consider normalized symmetric polynomials. And for this, they have to understand the image of the normalized Vandermonde map at infinity. And then they see that it is actually the same as understanding univariate probability measures on the interval 0 to infinity. And yes, then they have a lot of nice properties about symmetric polynomials, norm symmetric polynomials at infinity, normalized symmetric polynomials. And we are still writing on it. It should be on arXiv also in the next few weeks. The four of us will upload another paper where we consider the dual side of this. So where we consider now symmetric non-negative polynomials at infinity and symmetric sums of squares at infinity. And yes, search some advertisement if you're interested. And thank you a lot for your attention here in this talk.
Okay, thank you very much for your talk. Do we have questions from the audience?
I might have a random question. Hopefully it's not too off topic. So, yeah, I was just curious about so you mentioned this result where the boundary of pi and b and that of the cyclic polytope, you have the diffeomorphism. So I was wondering, like, maybe other than like this thing about the hook-shaped symmetric form and the copositivity, like, is there any place where you use the fact that there's actually like a diffeomorphism and not something weaker?
So do you mean some application?
Yeah, some application where you actually use the fact that there's a diffeomorphism rather than something like a weaker relation.
No, not really. So
Okay.
also not in this copositivity of hook shapes. So this is just the statement, the theorem that it has the combinatorial structure of a cyclic polytope.
Yeah.
So but
So it's really just about the combinatorial structure. Okay.
Yes, only about that. But maybe there are some applications.
Okay.
Be happy to know.
Okay. More questions? Doesn't seem to be the case, so I will stop the recording.